Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientist with me, Sue Marchant, and Dave Ansell. Good evening, Dr. Dave.
Good evening.
Have you got anything that's exciting in the world of science?
This is yet another new type of TV display.
Yep.
So you've got the sort of old-fashioned CRT monitors, the big, deep ones. You've got the plasma displays, which are a bit like flat CRT monitors. You've got LCDs. And now you've got LPDs, which are laser phosphor displays, which is a wonderful name.
Gosh.
And these actually work remarkably...
I can just imagine somebody saying, hello, would you like to come and see my laser phosphor display?
It might work.
Yeah.
Anyway, these are, in fact, remarkably like the old-fashioned CRT displays. The way those worked is you'd fire electrons from the back of them, from a thing called an electron gun, and they fired to the front of the TV, and they'd hit something called a phosphor, which when they got hit by electrons, it would glow.
Right.
So what they've done with these laser phosphor displays, they've sort of taken it back to front. And instead of using electron guns, because that you need to have a vacuum, they use a laser. So you have an ultraviolet laser sitting in your room, firing a laser at the screen, which has got lots of these phosphors. When it gets hit by the ultraviolet light, it glows. Just like the way if you've ever been into a club or a disco and your clothes start glowing.
Right.
When ultraviolet light shines on you, on the fact that they're called optical brighteners in your clothes. It's the reason why washing powders say whiter than white.
Right.
It's because they take in ultraviolet light from the sun and they glow, so your clothes are actually glowing, so they're even brighter. But instead of you have three different colours of phosphors, and you can build up a picture by shooting the laser across the screen. Because it's just a printed phosphor display, you can make them very big. And because it's not wasting energy, like an LCD, which actually cuts out 2/3 of the light, it should be a lot more efficient.
Now it is time to go to the phones first of all now, Dave, with our first caller. And I believe we've got Ian there. You're through to Dr. Dave. What's your question?
I'd like to ask you about electricity.
Yeah.
It's to do with a consumer unit in a domestic situation. And I wondered if you could just briefly tell me the difference between an MCB, an RCBO, and their appropriate functions.
The MCB is a miniature circuit breaker.
Yeah.
Which is basically just a fuse. It's a fuse which you can reset by flipping the switch back. So if too much current flows through that part of your house, so if, for example, you had a short circuit in your kettle, so the two wires touch together, you get huge current flowing through that.
Right, gotcha.
And that can cause fires and things. So mostly those are there to stop things overheating, stop the wires overheating, catching fire and your house burning down. Right,
what about earth faults on MCB? Does it work?
I don't think, from the way they're wired, they can do, because they're just wired straight in line with the live wire.
Right, mate. What about the RCBO, with a residual circuit breaker with overcurrent?
Yeah, OK, so that, with the overcurrent, means that's a fuse as well. So if you draw far too much current through that, it will trip out as well.
Gotcha.
With an electric circuit, you've got a wire going in and a wire coming out again. And it detects a difference in the current between the stuff going out and the stuff coming back. And if there's any difference, some must be leaking out to Earth somewhere. Gotcha. And that could be through you. So it will trip out with a very small leak to Earth, because there should never be a leak to Earth. So that's the thing which actually stops you getting killed if you stick your finger in the power, if you're lucky.
If you're down the bottom of the garden doing a bit of mowing with your electric mower, and you've got, say, 100 metres of cable, am I right in saying it'll take a little bit longer to trip out?
Electricity basically flows at about 0.9 of the speed of light, and the speed of light is about 300,000 kilometres a second. So unless your garden is several thousand kilometres long, it's not going to make any difference.
Thank you very much, Dave.
Cheers.
You're welcome. Thank you very much. Take care.
Bye.
Bye-bye. Bye, Ian.
Ta-da.
He was doing his clearing up, you see, as we went through that. All right, let's go to our next question now from Sue, who sent a text in. She says, why is it that in the extreme cold, if you throw a glass of cold water in the air, it falls as water, but hot water falls as snow or ice crystals? Oh, I've never done that, so you must have been to Antarctica. But that's the question, Dave. What do you reckon?
Ooh, that's an interesting one. I can't say I've done the experiment exactly. Certainly it can get cold enough that if you throw boiling water up into the air, it'll come down, and it will come down frozen. The only thing that I can possibly think of is that if water is very, very hot, it has less surface tension. And surface tension is the thing which pulls it into droplets. And so if water's quite cold, it's going to have more surface tension, so when you throw it into the air, it will tend to form bigger droplets, which will cool down more slowly. Whereas if it's very, very hot, when you throw it into the air, it's got very little surface tension, so there's very little to stop it breaking up into very, very small droplets, which will cool down a lot quicker. And also, if it's got a very large surface area, basically the heat will get lost very, very quickly through evaporation, if nothing else.
Let's go to our next question. This time by email, and this is from Martin. Hello, Martin. He sent an email in saying, why do bus windows mist up? It's really irritating, I know, Martin, I agree. So, Dave, why do they mist up?
Yeah, it's kind of strange because a bus seems much bigger in area than a car, but still the windows seem to be running with water very, very soon. If you think of a vehicle as a closed box, where's the water coming from? All the water's coming from is the people. When you breathe, your lungs are damp, and so you've always got water evaporating off your surfaces on your lung, so you're breathing out lots and lots of water. So for a start with a bus, you've got lots and lots of people. So you've maybe got 50 people in a bus. And where's this water vapour going? It can either get out holes, so with a car there's quite a lot of ventilation, so you're sucking a lot of air in, and it's blowing through and escaping out of vents at the back. And so the car's it's quite good for getting rid of water, but in a bus there's probably not 50 times as much ventilation as there is in a car. For a start, you've got less places for the water to go, and also per person there's probably less window in a bus. So you've got lots and lots of very moist air in the bus because of all these people breathing. There's not that much airflow through it. So eventually that water vapour is going to build up until there's enough water vapour in the air to condense on the windows, and it just keeps condensing and runs down the walls.
There's a text here that's come in from Mike. He says, I watch YouTube, the Kitty Hawk aircraft carrier ploughing through 90-foot waves. How do they test such ships to cope with huge seas? Do they use models in tanks, or what do they do? Dave?
Certainly until very recently, the main way of testing it was, yes, with models in tanks. So you can build a model of the ship. There's a great big naval one, I think it's possibly somewhere west of London, with a great big long tank, and you can make waves in it. Then you can drive your model ship down there, and you can put little sensors in it to measure how big the forces are. And you can then work out whether the forces are any bigger than other ships you've built, so whether it's likely to fall apart. And there's a lot of experience they've built up by looking at ships and seeing which ones work and which ones don't work for the last 2,000 years. And slowly you make the ship. They tend not to start off with a little ship, then make a huge one, because then things go wrong. But generally, if you make the next one a little bit bigger than the last one, and if you start to see cracks in the last one, you sort of make the next one a bit stronger there. They do sometimes get it wrong. If you've ever tried snapping a piece, if you pull on a piece of paper or something, it's very, very strong unless you put a little tear in it to start with, when it will crack really easily. And tear very easily. During the Second World War, the Americans were building Liberty ships incredibly quickly, and the problem was they had very sharp corners on the hatch covers, and therefore you got cracks forming from these hatch covers. And several of the Liberty ships just fell apart in fairly low seas just because these cracks formed at these weak points, and the ships fell apart. And so after they worked out what was wrong, they built ships which didn't have, they put very rounded corners on the hatch covers, and ships tend not to fail in that way anymore.
If you're enjoying Ask the Naked Scientist, then you might like to check out The Naked Scientist, our regular roundup of the world's best science. Each week we take a look at the latest science news, talk to top researchers working at the coalface of discovery, and also get our hands dirty with a science experiment that you can join in with too. So make it a date and prepare to strip down science on the web at nakedscientist.com/podcast. Got an email here from Ken, who's in Hawaii. Wow. He says, I live in Hawaii, you lucky thing, Ken. All the islands here are volcanically formed. The Pacific plate drifts over a hot spot from deep in the earth. What is the hot spot, and are there other ones?
A hot spot is an area where you're getting lots and lots of really hot rock coming up from really deep in the earth. Basic structure of the earth is you've got the crust on the surface, which is the rock which is still solid. And that is in the middle of the oceans, maybe 5 kilometres thick. And below that you have a thing called the mantle. And this is an area of semi-molten rock. If you hit it with a hammer, the hammer would bounce off, but over thousands of years it will sort of flow. And this is several thousand kilometres deep. It goes most of the way to the centre of the Earth, and in the middle there's a core. Now, this mantle convects, so you get areas where you get upwellings in the mantle with very, very hot molten mantle coming upwards, and this is where you get hot spots. These seem to be independent of the way the crust is moving, so the crust is moving around the place as well. And in fact, the crust moves over the top of the hot spots in the case of Hawaii. So in Hawaii, there's a whole line of islands, and that line of islands is actually where the crust has moved over the top of the hot spot over millions and millions of years. And so you get a volcano over the top of the hot spot, it gets bigger and bigger and bigger, and then the crust moves off too far to one way, and you get a new volcano further along in the line. And there's a string of 10 or 20 of these islands, if not more, if you look at it underwater, all formed as the crust has slowly moved over the hotspot. There's lots of them, actually. Famous ones include Iceland. It's the middle of the ocean, and the reason why it's there is because you've got this upwelling of lots and lots of hot rock. In the Great Rift Valley, there's a hot spot which is thought to be melting the plate which makes up Africa, and because Africa's being stretched slightly for other reasons, it's slowly stretching, and it's probably going to break Africa in half over millions of years. And it probably wouldn't have broken there if you hadn't got a hot spot coming up underneath. So yeah, there's lots and lots of hot spots all over the place, and you're sitting on one of the most famous ones and most kind of cleanest ones.
In Hawaii?
In Hawaii.
The thought.
Jealous,
I know, yes, I know. Right, let's go to a question now that has come in, and that is from Mike in Colchester. I was watching a fascinating programme on the pyramids, and they said the blocks of the pyramids were made of limestone. What are the properties of limestone that builds such amazing structures, as I thought water would go through it? Dave?
Limestone's an interesting rock from the point of view of building things out of it, because although it can dissolve in water, and so you can over tens of thousands of years you can dissolve it out, and it forms caves and stalactites and stalagmites and things. It's actually a very, very strong rock. Because it will dissolve. So if you've got a lump of limestone sitting underwater, you get bits of limestone dissolving in one place and redepositing in others, and that tends to sort of concrete it all together. So you've got something a bit like cement gluing it all the little bits of rock together. It makes a very, very strong, very, very consistent kind of rock, or some limestones are anyway. And that's why they're actually the favourite building material, or things like Portland stone is a form of limestone, and most of London has been formed by hollowing out Portland Bill. The rock on the end of Portland Bill is now a lot smaller than it used to be because it's all been built into London. Lots of the buildings in Cambridge are made out of other limestones. King's College Chapel is all limestone. Basically, it's a really nice, consistent material. You can carve it nicely, and it will get affected by chemical weathering, and so it will dissolve over a very, very long period. But actually, if you build something the size of the pyramids, or especially the Great Pyramid, it's a huge, great thing. The rate at which it will dissolve is very, very slow. It would take hundreds of thousands of years for that to be an issue. And other rocks, things like slates or shales and things, would get broken up far, far quicker and just fall apart and get washed away. And so limestone is a very good building material.
Excellent. Our next question comes by email from Dave. He says, Dear Dr. Dave, it's all Dave's tonight. I have read about a fluorescent tube being illuminated if placed under an electricity pylon. Is this possible? If so, does this principle work? And does this mean it is safe to be nearby? Good question.
I've seen it done on TV, certainly. I see no reason why it doesn't work. I've lit up fluorescent tubes in various other things. If you go near a Van de Graaff generator, you can light up a fluorescent tube.
Wow.
If you rub it vigorously enough with a sort of woolen cloth, you can get flashes of light out of it.
Wow.
Even if you just if you charge up a balloon on your hair and then move a balloon near, in fact, just a compact fluorescent light bulb, move it in and out near a normal fluorescent tube or a light bulb, it will get little flashes of light out of it. The reason is the way a fluorescent tube works is you've got very low pressure mercury gas inside, actually. And some of those atoms, electrons have fallen off them just randomly. And if you apply an electric field, that means electrons are negative, so you put a negative balloon at one end of it. All the electrons are repelled by the negative balloon, all the positive atoms are attracted towards it. And as electrons run away or get pushed away from it, they bash into other atoms and knock off other electrons and so on and so forth. So you get lots of what's called ions flying around and bashing around and giving atoms energy. And the mercury atoms give this energy out as light. In fact, they're specially designed fluorescent tubes so that very low electric fields will do it, so they're nice and efficient. And near high voltage power lines, there are fairly powerful, fairly high electric fields by the standards of a fluorescent tube, and it will light up. In fact, long fluorescent tubes light up much more easily than short ones. If you've ever seen someone doing it, it'll always be a long one. And is there a problem with these electric fields? There's been quite a lot of research done on this, partly because lots of people have decided that it's a problem and lots of people think that they're sensitive to it, that people have done experiments with them. Lots of people think they can feel electric fields and they can't. If you put them in a room and they say they feel awful when there's electric field, and you turn electric fields on and off and ask them when they feel awful, they aren't related at all. And so as far as we know, there's no actual problems with electric fields. Quite often there are problems with pylons, because pylons tend to be in the nasty part of town, and people in the nasty part of town, there's lots of pollution, they're ill otherwise. But as far as definitely living a couple of 100 metres away doesn't seem to be a major problem. Personally, I wouldn't want to live right next to them, because you might get some charged lines, not really from the electric fields, but just because you get a few sparks off the end, and it might cause some issues. But definitely, if you're a reasonable distance away, it's not a problem.
As a scientist, you see, you're in the face of danger all the time, aren't you, Dave?
I've produced much nastier electric fields in my garage regularly.
Do you? Dear. All right. Now then, Dominic has said, why don't oil paints wash out so easily, and what is so special about the White Spirit who needed to remove them?
OK, it's all actually down to, if you ever tried mixing oil and water, if you ever tried making salad dressing or something, if you mix vinegar, which is basically water, and oil, they don't mix together. That's actually because water molecules really like other water molecules, and they don't really like oil molecules. So the water molecules stick together and push out all the oil molecules, so they don't mix together, they're immiscible. And oily things will dissolve in oil. Things which like water will dissolve in water. So oil paints tend to be made out of things which dissolve in oil. Which means they don't dissolve very well in water. And water-based paints tend to be made out of things which dissolve in water, but they don't dissolve in oil. So turpentine and white spirit are oily things, so they'll dissolve things which dissolve in oily things well, but water won't. Modern paints also, they tend to put a sort of plastic in them, so the plastic will set as it dries as well, so they won't, once they're set, they won't dissolve in either.
All right. Now then, let's go back to the emails now, because Linda has sent one in to say, how does one really balance on a bicycle? It feels easy, but it looks impossible once you've never tried it. That's true if you get back on a bike, after some years of refraining from riding one, then it does seem to be a little bit scary. So, Dave, how do we really balance on a bicycle?
There's various effects. Basically, the fundamental thing is that if you start falling over to the right, if the handlebars turn to the right, then you turn a corner, the bicycle sort of drives itself back under you, because the wheels will move to the right because you've turned to the right, and if they get back under you, then you'll be upright again. Right,
yeah.
So it's all about what's making the handlebars turn to the right. There's three things which could be doing that, and I think it's a mixture of all three. One of them is your hands, and it's the reason why it takes a while to learn to ride a bike, especially at very low speed. It's almost entirely your hands. Basically, if you start falling over to the right, you automatically turn the handlebars to the right with your hands, and so you steer yourself upright again. And in fact, if you want to turn around a corner to the right, you tend to lean to the right before you want to turn around the corner, so as you don't fall over. Because if you didn't lean over before you turn the handlebars, then you'd actually tip over to the left. Okay, so one thing is your hands turning to the right, turning the handlebars. Another one is that if you've ever tried wheeling a bike by the seat, if it tips over to the right, you'll notice that the wheel will fall over to the right as well. The wheel falls in the direction it's tipping. That's because the front forks aren't vertical, they're sort of heading forwards. And that means that it moves the point at which they touch the ground, and that means they just will tend to fall in the direction which you're tipping. So that will help you stay upright as well. And the third thing is, I don't know if you've ever played with gyroscopes. So if you
some time ago.
Gyroscopes
some time ago.
These are basically if you get something spinning, you have this really strange effect that if you push it, try and twist it in one direction, it will actually end up moving at 90 degrees the direction you twisted it. Which is the reason why gyroscopes don't fall over. Yeah. Because instead of falling over downwards, they actually end up moving sideways. And in fact, the third thing is that gyroscopically, if your bike turns to the right, the gyroscope effect on the front wheel will turn the wheel in and get you upright again. And gyroscopes are stronger the faster you go. So it's easier to ride a bike if you're going fast. In fact, if you're going very fast, it's actually very hard to turn the wheel at all. And if you're going very slowly, it's almost entirely your hands moving the handlebars, and so it's much more difficult if you're going very fast. Then the gyroscopic effect will work. So there's 3 different things which are used in varying amounts depending how fast you're going.
Gosh. All right, well, we've got Ted on the telephone.
We have a lot of snow recently and seem to have different types of snow, so they tell us. Some are more wet than others and some cause more problems than others. Is there more than one type of snow?
Yes, there are lots and lots of different types of snow. The first big difference is depending on how wet it is. If the snow's falling when it's quite warm, then the snow's sort of melting a bit all the time, and so the snowflakes tend to stick together because there's a thin layer of water on the surface. And so they tend to stick together, and if it's just melting a little bit, it tends to stick together and make good snowballs, so you get good snowball snow.
Right.
If it's very cold and it doesn't melt when you stuff the snowballs together, then they don't stick. Sometimes when it snows, I remember as a kid it once snowed and it was so cold that you couldn't make snowballs. I was incredibly disappointed, especially as I grew up in Devon where it never ever snowed, not one bitter. The other thing is actually if you look at the individual snowflakes, they can be different shapes. Depending on the temperature and the humidity and how fast the snowflakes formed. You can have everything from the standard snowflake, which everyone makes at Christmas time with the 6 pointed stars with all the kind of little bits coming off it, to little rods, to little just straight hexagonal discs, to hollow tubes. So all sorts of different types of snowflakes you can get, and all of these will have slightly different properties when they pile up in a great big pile, and how they stick together and how they interact. So yes, there's lots and lots of different types of snow.
You can have a snow shop.
Well, yeah. I mean, when they put salt on the grit on the road, then does it need different salt, different grit? Obviously not, no.
No. Basically, the grit works by reducing the melting point of the snow. So if it's -2 out there and you put enough grit on it and it changes the melting point to -4, then the snow will melt and will run away somewhere else.
Okay.
And so that will work on any kind of ice or snow. The reason why you sometimes get the wrong kind of snow is if you get very, very fine, powdery snow, it can sometimes get places where it wouldn't have got otherwise. Or if you get really sticky snow, it can kind of pile up on things and make power lines fall down.
All right.
Yeah, thanks very much.
Thank you, Ted. Take care. Bye-bye. Now, one here that's come in by email from Derek. He says, is it possible to manipulate the weather? I asked this because my elderly aunt told me of some tests they were doing to make it rain. This was just after the Second World War. Have there been any other tests in this world? I think they did something on the Olympics, didn't they?
Yes. The Chinese are very big on this sort of thing. I think the Russians were as well. One of the things which you can do, if you have a cloud which is almost starting to rain, basically it takes a long time for the water droplets to get big enough and grow bigger and bigger and bigger, because there aren't very many places for the water droplets to start. So it can take a long time for the water droplets to get big enough to fall out of the sky. So what you can do is you can help that process along by dropping something into the cloud. Silver iodide is a favourite for some reason. I think probably it's very strongly attracted to water and it makes very fine powder. So you go up with a plane, you drop silver iodide powder into the cloud. That triggers the formation of lots of raindrops. And so the rain drops earlier than it would have done otherwise. So the Chinese drop silver iodide into clouds so that it rains in one place and not on Beijing during the Olympics, for example. Sometimes it's very hard to know whether it works or not because weather is very variable, and you didn't ever know what the weather would have done if you hadn't dropped the silver iodide into the cloud. So it's hard to know what would have happened. They think also it can sometimes behave unpredictably, and they think that Beijing, I think this last year, suddenly got about sort of 12 inches of snow all of a sudden, if not, I think maybe even more than that, incredibly heavy snow, and they think that might have been related to them dropping silver iodide out of the clouds. I think actually the silver iodide is a very similar structure to ice, so it triggers the formation of ice crystals, which then fall down and end up as falling as rain or snow. So yeah, that's a major way in which they've been trying to change the weather.
Scary stuff, if you ask
me. They tend
me.
not to do it in democracies, because what happens if someone gets a huge amount of rain dropped on them and it causes floods, then the person who tried seeding the clouds like this tends to get sued.
We shouldn't be messing with nature, that's all that I can say. We've got time just for one more question. Dave, would a magnetic wall attract a bullet?
It sort of depends what your bullet is made out of. Most bullets are made out of lead, sometimes with a copper jacket on the outside, and lead isn't magnetic. So it certainly wouldn't be attracted by the wall. In fact, what would probably happen, it would be repelled, because if you move something which conducts electricity, like a metal, into a magnetic field, it will induce an electric current inside the metal. That forms an electromagnet which repels. So I would have thought the bullet would be repelled from the wall rather than attracted to it.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.